technologies such as the DAW and OSC, Adrian has contributed to the emerging field of E-textiles. His talk today will demonstrate many interesting re-implementations and new designs of Soviet-era ICs. Please welcome to the Hackaday Supercon stage, Adrian Freed.
So I'm going to be talking about some of the chips I've collected in the last few months, and the first thing I want to point out is that they're made from all over former Eastern Bloc, not just Russia. In fact, very few of them are made in Russia. So we've got Czechoslovakia, Belarus, Poland, Romania, and Latvia, Lithuania. And in case you're wondering, I don't have any trouble getting these chips, so even though some of them may not be being made anymore, but there is one company, at least I found, that makes amazing, interesting chips. They're called ARPA in Latvia. For anyone who's been involved in Eurorack synths or old analog synth designs, you know the importance of this design, the LM13700. It's all over synths, and they noticed that the amplifier built into that, which is a very simple Darlington output, is never used in those designs because it's offset. So they made this nice chip, which has 4 operational transconductance amplifiers instead of 2, is in a smaller package, and they just eliminate it because everybody uses an op-amp buffer. And this is being built these days into a lot of interesting synthesizers. So I'm talking about stuff from the past and that is relevant now. But there's an elephant in the room. We're all suffering from a bad regional conflict. The closer you are to the conflict, the worse it is. I'm going to defer conversations about that till afterwards. I'm happy to talk about the technopolitics and the politics. But I do want to point out that one of my ways of contributing is to trade with people there because they need the money. And so these are some of the envelopes that came back for some of the chips from, you see Bulgaria, Ukraine, Latvia in this particular, but I've been buying from all over. So here's the first, this is how I got into this in the first place. This is a famous, it's one of the earliest hands-on, easy to build, interesting electronic instruments. It's from Michel Weizfitz. And basically you put your body in the circuit of an op-amp. And notice this, the 709, it's built on an old obsolete chip, cannot be replaced with some other op-amp. And that's because it's uncompensated. All this op-amp wants to do is oscillate because it doesn't have a compensation capacitor to prevent that. And when I was teaching students, new generations discover the circuit and they want to make it, but where are they going to get this 709? And I discovered they're easy to get from former Eastern Bloc places. And we don't have access to the video for that. So let's just go to the slide. There we go. So it turns out that that 709, this is one of the prejudices or biases that was implicit that I didn't know I had implicitly, which is, things from the West are the best, things that you know about, things that in languages you know about must be better than things from other places, which are probably copies. There's a sort of, I don't know where this comes from, but we often have this kind of bias. Turns out that they were re-implementations. They weren't copies of the mask. And this is that guy Zepto Bars that produces these beautiful chip things, and you can see the differences. And so these are 2 different implementations of that 709. And the other claim was that it had to be a 709. And I was delighted to discover this chip because it's an uncompensated op-amp. And you don't need those extra transistors because it's got a power output stage and heat sinks built in. So, well, I can set this up so you can play it afterwards, but a smart thing to do with an interface like this is to hook the speaker up into your tube to get some low frequencies, and that's a fun little touch instrument. And there are lots of other uses of a dip, easy to prototype with power op amp. And I have about 20 of them with me. If anyone wants to do something, I'm happy to share those. So that's my circuit, which I'm calling the power crackle. It doesn't have those output transistors to buffer the speaker. You can go straight to the speaker. Oops. So while I'm on that package, turn my badge on here. There we go. Oh, I should run it, right? On a good day, these would flash. Anyway, I have one of these set up. It's got 4 high current transistors on it, already with a heatsink for you, easy to use on a breadboard, and I have it hooked up to the badge. And also, I've been able to drive Nixie tubes and stuff with it. And let's just skip that one. So while we're still on the subject of op amps, the Polyvox circuits are really popular. They're very odd. It's called active R. There's no capacitor, and yet you can build very wide range sweepable filters by dropping some current into the bias of the op amp. And that's because these op amps do have a compensation capacitor that limits their bandwidth. But that bandwidth limitation's dependent on the bias. So you have a fantastic VCF, very distinctive sound. And so that's another well-known circuit that's sought after that you can buy on eBay. And I found one that's kind of obscure. It's out of Eastern Germany. And the thing that caught my eye is the star on that capacitor there, because one model of this op amp doesn't have the compensation capacitor. And this is unique as far as I know, this op amp. It's the only op amp you can buy that has offset adjustment, external. That's the 2 pins on the bottom left. It has the bias control, so you could sweep and use it as an active R, but you can put your own capacitor in and choose the time constant. So all 3 key parameters of the op amp are controllable here. You know what manufacturers of op amps have done? They've said, we can get 4 op amps in the same package. Let us do the offset compensation. Let's sell you 100 variants depending on the bandwidth, and they just change that capacitor. And let's sell them in a whole range of power consumption. So you end up with 10,000 op amps in your catalog when we really only need 1 and some external components. So if I was stuck somewhere and someone said, what op amp do you need 100 of? It would be this one. It's kind of a universal op amp with bias current, offset compensation, frequency compensation, all accessible from the outside. And for teaching, it's amazing because these compensation nodes get you into each stage. Every op amp has 3 stages, right, of amplification, and you've got access to all those nodes to play around with them. Switching away from op amps now, if you may know this, but digital circuits, you can build all things that are in digital computers out of NAND gates or NOR gates. You can build up everything, flip-flops, all the other gates. That's kind of the universal component. If you're building oscillators, it turns out the XOR is marvelous. That's what biological systems that have oscillators use as their main primitive. It's a biochemical XOR gate, but it does the job. I'm going to make a bold claim here. I have some backup, but I can talk to you about afterwards. But this is what you want. 2 shorted inverters will get you all the high-performance RF analog you'd ever need. That's what you want to be building on chips. So I do design chips, but I need to prototype them. So I've made a collection of all the digital CMOS chips I could find that were useful to do analog circuits. This is what I call perverse engineering. These 2 and some of these this bottom left corner was a problem because, you know, if you're a collector, you want to have everything. You want to have all the trading cards. And I kept, as I was exploring the catalogs of Soviet-era chips, I kept finding CMOS chips that they built that weren't in the 4000 series. And what they did for these two is they said, well, that's ridiculous. There's a 4000 series chip with 14 pins, and 2 of them are no connects. Let's drop an inverter in there. And that reminded me of someone who had the same reflex later on, which is the CD 4572UB. It's a pretty obscure one. But again, if I had to have one chip in the CMOS to play around with analog, it would be this one, because it's got 4 inverters, NOR, and an AND gate. And the way you design things with this chip, analog things, is a bit like this. Your first reflex is to short all the outputs together. So this is, you'll notice, all the outputs are shorted together. In fact, these two have the outputs also shorted to their inputs. And this has a couple of inputs shorted together. What is this? It's a 3-bit D to A converter. If you make sure that node there is mid-rail, it's highly linear. But what's interesting to do is not make it mid-rail, make it have a little soft, so it wanders a little bit, and that's where your output is. And so when you're using it in music and you drive a ramp up and down to make a triangle wave, it sounds like a pretty good sine wave. So by shaping that node, you can get a triangle wave. By ramping it up, you can get a sawtooth. Very flexible out of a single 20-cent gate. And that's exactly what you do at scale in analog VLSI for RF. And for especially low voltage, because the whole thing about these gates, unlike opamps aren't a good primitive for high speed and low voltage rails because they stack the transistors and you can't get enough dynamic range. But so this is the way to go, parallel up gates. So that's a hint for anyone who wants to do analog with the chip stuff going on. Let's take a look at inverters as your primitive. Here's a weird one. For those of you who looked at 4000 series may have noticed that the beginning of CMOS was very troubled. In fact, it's named the 4000 series, but nobody uses the 4000. They stopped making it. They stopped making the 4006. Hardly anyone uses the 4000. I mean, it's a mess. The XOR gate was a disaster. This is the 4030, and they quickly realized it was a disaster and put out the 4070 as a replacement, and then sold 4030s, which were actually 4070s renumbered. Turns out this is the one you want to do interesting things with, the 4030, but it hasn't been made in the West in decades, but it's still readily available in its Soviet-era counterpart. Why does it suck as a logic gate? Because one of its inputs goes, inputs usually go into gates, but here it goes into the drain. And so the capacitance here, not only is it bigger than the other node, but it varies. So this is a very glitchy digital circuit. So what they did is they just stuck inverter buffers on the front in the 4070 series. So I got really into this, like, okay, let's do a circuit with this. And the problem was I bought from all over the former Eastern Bloc, I bought flavors of 4030s, and they were all different, and some of them were 4070s in disguise, and some of them weren't. So this is a circuit I designed to tell the difference, and then, of course, you have to actually lay them all out and try them. The ones with an X don't oscillate. That single gate fed back to itself doesn't oscillate. That's because it doesn't have 3 inverters in a row. It doesn't form a ring. So we know that's the one I'm looking for to play games with analog. We also find some interesting things out, like there was somewhere, I'm not sure where this one is actually from, this is probably made in the Ukraine early on. It'll only run at a megahertz, that the 3 XOR gates in the ring, whereas your typical ones are running at 5 megahertz. Modern CMOS This one is 90 megahertz, this one's 47. Of course, when you're doing this on a chip, you can get to gigahertz with these circuits. So yeah, there's still innovation. The 4000 series and CMOS in small pin counts is not gone away. This is the latest chip from TI. It has Schmidt triggers on the import and the XOR, and it's all kinds of interesting things to be done there. So why do I go to all this trouble? Let's see if we can get this video to play. So that's a voltage sweep on one of the input gates of those 3 XORs in a ring. So it's 3 caps, 3 XOR gates, and you're modulating digital input. And we've got a wide range VCO, much wider than I know really how to make with a ring oscillator. And it's got 3 kinds of chaotic oscillator behavior when you really starve it of voltage, which you heard at the end. All this stuff, you saw bursts of noise, it's called intermittency. So it's these hidden features that I'm looking for music, but also because it tells me a lot about when I go to design analog chips, what I need to look out for. In fact, in RF, you need to make high-frequency ring oscillators which don't have chaotic behavior. So we need to understand what it is, and I have a really cheap circuit, so long as I can get the old 4030A, which is rare as hen's teeth, or the easily available Soviet ones. That's it. Do I have time for questions? I started late, but yes. Any questions? Oh yeah. Yeah, the video unfortunately wouldn't play for that. So I like to use a 3-terminal neon that's very bright because it's actually a trigger tube. And you can do things like Thyratron. You can build ring oscillators, you can build counters with it if you've got 70 volts available. And you can build all kinds of old interesting circuits. But the nice thing, if you're showing and introducing people to neon circuits, is it's really bright. You can put a lot of current through it. It's quite big. So in the demo that's missing, which I'll make public online, I'm just running a binary counter and using it as an indicator. But there's lots of other things you can do with that. Yeah? The real win was discovering that a lot of these chips were made in East Germany, because I have enough schoolboy German to get by there. The other thing is the data sheets are, for the most part, they're numbers, right? And you just have to know that B is often used instead of V, and there's some for voltage. So you can get through that way. The other thing is they use block diagrams. And if you already get a hint of what it does, and then a much better answer to that is this is an excuse to go meet some people from other parts of the world and ask them questions and what they do with these chips. Yep. Yes. The quick answer is yes. Also, there are lots of data books and data sheets and websites with equivalent tables of equivalence with chips you know and chips with their part numbers. And that's how I discovered all the missing chips that are interesting, because they list ones that don't have a Western equivalent. I'm like, okay, I got to start looking at what that one is. And that's when I discovered that my bias that, oh, they couldn't invent anything there was complete nonsense. There's a whole bunch of really interesting chips. In fact, in that era, they were ahead of the rest of the world in ECL performance. That's the chips that the Cray was built with. They had faster ECL, and they had better germanium at some point. So, you know, it sort of opened my mind to look at these things for what they are, not what we might think they are, which is foreign and other. Definitely worth learning about. Yeah. eBay is the only one that can transact reliably in all these countries. And interestingly, I was able to find all the chips, including ones made in Russia, but you can't buy anything from Russia through eBay. So it's a sort of interesting time. The big mystery to me is there was a period where you couldn't get them very easily. Now there are so many of them. I don't know where they or how they were stocked, or I actually think there are some fabs still running. And that, you know, that's more research to do, but you don't have to worry, at least if you're hacking, about supply, because you can find these things. And I have never had an instance of one not working. And a lot of these chips, they have the dates on them. Some of them are back into the 70s. So the packaging and so on was solid enough. Any other questions? I have a lot of the chips, happy to share them. Yeah. Well, one thing that's interesting, I mean, is that 709. The 709 came out, it was quickly replaced by the 301 and 741 in this kind of logic we have of obsoleting and replacing. But that's not what they did. This company called Tesla, interesting, which had a lawsuit about the name, they make the 709 in 3 grades. As I said, they were, you know, you might say, well, why did they bother making them? If they could make their own, why didn't they do all their own designs? Well, the reason is they wanted to use some of the schematics. It's for the same reason they built, and people call them clones or copies of the CPUs, but actually a lot of them had new interesting instructions and better firmware, but they had to be like ones in the West because of the software. That's what they were looking for. Yeah, and there are some interesting things to look at. I didn't talk anything about the CPUs. That's a whole world too of interesting stuff. Yeah. Yeah, let's see if I can get that going. Anyone who's, oh, yeah, hang on. So there are 7. Part of the mystery of this instrument is it was designed specifically to be hard to play and unpredictable. It's part of the charm. And since I haven't spent the year or two that Michel Weisfitz spent tuning the components to give the most wildness, so that's something you can all try to do. It's a really easy circuit to build. Yeah, it's hard without, this is so much louder The other thing about the Crackle box is the ideal environment is 10 people, all of whom have a Crackle box in a room playing for each other. It's really quiet. It's like a parlor instrument, but it's pretty easy with a power op amp to make this loud enough as a bigger instrument. Thank you. Thank you. Hey, how badly have I knocked off the schedule? Sorry about that. Perfect.